Now next topic, that is properties of scalar product of vectors. Now this is very important thing, because the properties of scalar product of vectors, that is very useful to solve different problems as well as MCQs, right? Now see here, first thing, the commutative law. We write A dot B, that is AB cos theta. So we can write it as BA cos theta also. So that is B dot A. It implies that we can write A dot B, that is equal to B dot A. So we can say this thing, the commutative law holds for the scalar product of vectors. Then after, the distributive law, right? Suppose we have A dot B plus C. Then simply we can simplify it like this, A dot B plus A dot C, right? So distributive law also holds in the scalar product of vectors, okay? Now suppose A and B are parallel to each other. If A and B are parallel, means theta, that is 0. So if theta, that is 0, then cos theta, that is cos 0, that is equal to 1. So in that particular case, simply we can write A dot B, that is AB. Clear? Now suppose we take A dot A, then vector A dot vector A, that is simply we can write A into A, that is A square. So we can write magnitude of A, that is under root A dot A. It implies that if we have vector and if we want to find its magnitude, then easily we can calculate it with this relationship. Okay? Now, magnitude of a vector is equal to the square root of the scalar product of vector with itself, right? Then after, if A and B are perpendicular to each other, if A and B are perpendicular to each other, then theta, that is equal to 90. So A dot B equal to AB cos theta, that is cos 90, that is equal to 0. It implies that here A dot B, that will be equal to 0. So if two vectors are perpendicular to each other, always their dot product will be 0. Or in other words, we can say, if dot product of two vectors comes to 0, then we can say these two are perpendicular to each other. Okay? So scalar product of two mutually perpendicular vectors, that is always 0. Clear? Now, scalar product of unit vectors in Cartesian coordinate system. We know this thing, we have three axes x, y and z in Cartesian coordinate system. And we have I caret, j caret and k caret unit vectors in the direction of x, y and z respectively in the Cartesian coordinate system. So between these unit vectors I caret, j caret and k caret, how the scalar product is carried out. Okay? Now let's first think about I dot I. So here we can write, suppose we have I dot I. So magnitude of I caret 1, magnitude of I caret 1. Now angle between vector and vector itself, that is 0. So we can write cos 0, so that is equal to 1. So I dot I caret, that is 1. So similarly we can write j caret dot j caret and k caret dot k caret, that is also equal to 1. But suppose we take I caret dot j caret, magnitude of I caret 1, magnitude of j caret 1, and angle between I caret and j caret, that is 90. So this is equal to 0. So we can write I dot j that is equal to j dot k that is equal to k dot I, and that is equal to 0. And here we can write j dot I that is equal to k dot j that is equal to I dot k that is also equal to 0. Simple thing. Clear? Okay. Now see here. Scalar product in terms of Cartesian components of vectors, right? So in Cartesian component form we write the vectors A and B as vector A equal to AXI caret plus AYJ caret plus AZ K caret, and vector B that is equal to BXI caret plus BYJ caret plus BZ K caret. Okay. Now let's take dot product between these two vectors in component form. So A dot B. So in first bracket we will take vector A in component form, dot in second bracket there is the vector B in component form, right? Now here simply we have to carry out the calculations like this. First we have to multiply AXI caret with these three components. Okay, but here be careful, this particular symbol of dot will be placed between vectors only, because dot product is defined for vectors only. It is not defined for scalars or scalar and vector. Okay, so see here how we will write it. First AXI caret is multiplied with these three. So AX BX I caret dot I caret. Then AX BY I caret dot J caret. Then AX BZ I dot K caret. Similarly, multiply AY J caret with these three. So we will get AY BX J caret dot I caret. AY BY J caret dot J caret plus AY BZ J caret dot K caret. Then multiply AZ K caret with these three. So we will get AZ BX K caret dot I caret plus AZ BY K caret dot J caret plus AZ BZ K caret dot K caret. But here we discussed the scalar product between unit vectors. So from that, substitute the values here in this particular one. So here I dot j, I dot k, j dot I, j dot k, k dot I, k dot j will be cancelled. And this I dot I, j dot j and k dot k, that will be equal to 1. So we can write simply vector A dot vector B that is equal to AX BX plus AY BY plus AZ BZ. Clear? Now see, if we want to find the angle between two vectors are given to you in Cartesian component form, suppose, right? And you want to find the angle between two vectors. Now we know A dot B that is AB cos theta. So we can write cos theta that is A dot B upon AB. So in Cartesian component form we can write A dot B that is AX BX plus AY BY plus AZ BZ. And magnitude of A that is under root AX square plus AY square plus AZ square. Similarly magnitude of B that is BX square plus BY square plus BZ square. So here using this particular formula, easily one can find the angle between two vectors also. Clear? Now, suppose we have any scalar quantity, lambda, and we multiply it with A dot B. Okay? So here When lambda is a scalar quantity, then you can simplify this type of problem simply like this. Suppose first you take product of lambda with b, and then after if scalar and vector is multiplied, it is simple product and the resultant will be vector quantity because one vector is there. And then after take dot product of this new vector with a, or first multiply lambda with a, you will get a new vector, right? And then take dot product of it with b. If you multiply this one by lambda, you know magnitude of vector a will be changed, direction will not change. Clear to all of you? So this is the properties.